Hello, welcome to this sixth week, lecture 2 of radio astronomy. In this particular week, we have been a little bit light. We started off with a particular demonstration or simulation of how antenna radiation patterns can be derived using a package called NEC. This particular lecture, we are going to revisit on some sample problems on all the topics which have been covered so far in the past 5 weeks. We also held a live session and in that sense we gathered the reaction from the students, and based on that we thought this is the best way to move forward, and so we are going to revisit some of the concepts and try to address them using simple problems as before. Maybe we have been a little bit light on doing some more problems. It may be beneficial for students to understand the concepts. So let's proceed. So the first problem which we are trying to tackle here is that of electromagnetic radiation is emitted from a distant object with a frequency of 1.4 gigahertz. What is the energy of the photon and what is the wavelength? So we revisit the basic thing that energy E is given by h nu, where nu is the frequency. And also you can visit that nu is nothing but c over lambda, where lambda is the wavelength. So if you use these two concepts, that the energy is h nu and this is nu is c over lambda, we derive energy, and h is the Planck's constant, so that has a known value given over here, and we put the frequency. So that is 1.4 gigahertz. So 1.4 10 to the power 9 hertz, gigahertz. And that gives us 9.28 10 to the power minus 25. The next one is, given the nu, we have to understand the lambda. So use the second formula, and you just derived it is 0.214 meter, okay, or we can say 21.4 centimeter. So this should be very easy for you to tackle. Let's go to the next one. Consider a source, radio source, that is found to be elliptical. Apologies, just go back to the previous slide. Yeah, consider a radio source that is found to be elliptical. So it is elliptical in nature. Elliptical in nature, so in shape, with a major axis of 0.3 degree and minus axis of 0.1 degree. What is the solid angle of this source? So here we are discussing about if a source is elliptical in nature and it has a major axis and minor axis defined, then what will be the solid angles obtained by the source? This is a very useful concept because we often have derivations with respect to the point sources, but when it comes to the extended sources, we end up with trouble. So here the equation we use is that suppose the angular extent is theta, then the solid angle is given by this particular expression which we have done earlier. So it comes out to be pi by 4 theta square. Here in this case for the ellipse we have not, theta is not same, that's for a circular source. So we have theta major and theta minor. Now we have been given theta major and theta minor, that is 0.3 degree and 0.1 degree. Now what we will do is that we will convert the degree into radian. That's what we have done here. And once you put that into this expression, you get finally that the omega, or the solid angle, is given by 7.18 10 to the power minus 6 steradian. Again, a very simple problem. The third problem which we are encountering here is you use a radio telescope that has a collecting area of 1.2 meters square to observe a radio source that at a frequency of 1420.4 megahertz and a bandwidth of 2 megahertz. You measure a detected power of 1.2 times 10 to the power minus 19 watts. What is the flux density F nu of the source in Janskis? Okay. So first of all, 1 Jansky, we can again revisit this. So 1 Jansky given by Jy is 10 to the power minus 26 watts per meter square per hertz steradian inverse. Okay, that is already known. So this is 1 Jansky. Now let us define. So F nu is the flux density, that is dependent on the power over effective area over the bandwidth delta nu. Now bandwidth we already knew, that is equal to what? That is equal to 2 megahertz. And the central frequency is given and the power is given. Collecting area also is given, that is effective is equal to 1.2 meters square. So we plug all of them together. So the P is in watts. P is also given by 1.2 into 10 to the power minus 19 watts. So we plug that in. We plug all the other values. Finally, it came out to be 5 times 10 to the power minus 26. We do this scaling of 1 Jansky. So finally, we get 5 Jansky. So finally, the flux came out to be 5 Jansky in this case. It's a very standard problem. So we have an effective area of the telescope given. We also have the frequency of observation, which doesn't come in this particular picture. We have the bandwidth of observation, 2 megahertz, and then we have the detected power. Okay, and so we finally get 5 Jansky. Next question, we have a radio source at a distance of 20 megaparsec. Now 1 parsec is already given over here, is 3.09 times 10 to the power 16 meters. It's important to define a larger unit because the distance becomes too large in astronomical scales. So it's 20 megaparsec. So you can define 20 megaparsec is equals to, you can do the math by yourself. So 20 times 10 to the power 6 multiplied by 3.09 into 10 to the power 16. So roughly this should come out to be around something like of the order of 6 times. This is 7, 13, okay. So 10 to the power 23 kind of in meter scale. Okay. That's the distance. It's observed by a telescope having a collecting area of 300 meters square. That's given over here. The frequency is given by 22.2 gigahertz, so 10 to the power 9 hertz, and a bandwidth of 250 kilohertz. Determine, have a flux density F nu is also given by 20 Jansky, and is found to be a uniform circle with an angular diameter of 30 arc seconds. Okay. Now with that, those information in the distance is given by 6 10 to the power 23 meter. Okay. With that information given, we are supposed to figure out what is the specific intensity I nu, total power of radiation detected by the telescope, and so we need to figure out the P, the I nu, and the luminosity. Okay, so let's see how we go about this. So first of all, the source, substance, and solid angle. So we know that is 30 arc second. So we convert that to the it's a circular source. So theta major is equal to theta minor, 30 arc seconds, and it has so we do that, all of them, and then finally we get 1.66 into minus 8 steradian. So intensity is 20 Jansky is the flux over the solid angle. So finally intensity is given by this particular expression, 1.2 10 to the power minus 14 watts per meter square per hertz per steradian. Okay, total power detected is Fp is given by F nu times area of the telescope times delta nu. So we put those in 20 Jansky times 10 to the power 26. That takes it to Jansky 2 watts per meter square per hertz per steradian. Yeah, per Jansky. So, and then 30 meters, 300 meters square is the area, and 250 kilohertz is the bandwidth. So that comes out to be the power is given by 1.5 to the power minus 17 watts. Okay, simply just substitution. So the previous question, when we had the P and the A effective and the bandwidth given, we derived the flux. In this particular case, we have angular, not a compact source, but it's extended source, and we have been given the flux density, the angular extent. So we calculate the specific intensity from that, and then from the flux density we also calculated the power. The last one is the luminosity. So we express the flux density multiplied by the bandwidth and the distance. Okay, so distance is, remember, 20 megaparsec. So 20 10 to the power 6 times megaparsec. So 1 parsec is 3.09 times 10 to the power 16 meters. Okay, so that whole square is the luminosity, the distance to that. And so if you multiply this with times the bandwidth times the flux density, you get the total luminosity in this particular band as 2.4 10 to the power 29 watts. Okay. Question number 5. An alien civilization is at a distance of 7 parsec, uses radio antenna of the diameter of 100 meters, acting as a transmitter to beam a radio signal towards the Earth. So now you're using a radio antenna as a transmitter. The civilization converts 5 times 10 to the power 6 joule of energy into this signal, which is transmitted at a constant power 400 seconds, centered at a frequency of 1 gigahertz and a bandwidth of 1 megahertz in a beam with a solid angle of 9.3 10 to the power minus 6 steradian. So what is the luminosity of the beam signal and what is the intensity of the beam signal? So what do we have? We have a distance, which is nothing but 7 parsec. So 7 multiplied by 3.09 times 10 to the power 16 meters. Then we have total energy and then total time, and the frequency is given by 1 gigahertz. So 10 to the power 9 hertz, and delta nu, or the bandwidth, is given by 1 megahertz or 10 to the power 6 hertz. And the beam solid angle is given by omega equals to 9.3 times 10 to the power minus 16 steradian. Given those, we need to calculate the luminosity and the intensity. Let's see. So luminosity is nothing but the total energy over total time, and that is given by 50 kilowatt. Okay, total energy was 5 10 to the power 6, 5 times 10 to the power 6 joules, and it was beamed for 100 seconds. And B is the intensity. So now you have the luminosity. From there you know the area of the transmitting antenna. Yeah, its diameter is 100 meter. It's already known. So then you can calculate the area and the omega of the beam and delta nu. So if you put that, so I nu is L over area effective times omega times delta nu. Okay. Rewriting it again. So area times omega times delta nu. That is our I nu. If I put all of them together, so area already we know it is omega is 9.3 10 to the minus 6. Delta nu is 1 megahertz 10 to the power 6 hertz, and this is the area is pi times 50 meter, diameter is 100 meters, so radius is 50 meters square. That gives you 7.85 into the power 3 meters square, and omega, this is the solid angle, is equal to this. Okay, and this is the the delta nu, the bandwidth. Yeah. Okay, so that gives you the final answer to be, if you just plug it in. So I nu, the intensity, is given by this expression, 0.685 watt per hertz per meter square per steradian. So in the previous problem, we did the reverse one. We have the we calculated the luminosity from the flux density and the delta nu and the distance. So if you have a distance, so that you draw the sphere, and so you multiply that with the entire area and you get the luminosity. In this case, you have the distance, the bandwidth, the frequency, the solid angle, and you calculate the intensity and the luminosity. Luminosity was easy and intensity was derived from the luminosity itself. So let's go to the next one. An electric stove is turned off and the heating element of the burner turns back to black, but the stove warning light still indicates that the stove is hot. An infrared sensor is aimed at the burner, and the radiation at a frequency of 3.33 10 to the power 14 hertz. So it's quite high. 3.33 10 to the power 14 hertz was detected from the burner, having an intensity of 1.46 10 to the power minus 28 watt per meter square per hertz per steradian. Estimate the temperature of the stove. That was the question. So this is a question from the black body radiation, and we did a lot of sums, problems for the Rayleigh-Jeans laws, etc. So let us see. So given such a high value of the frequency, 10 to the power 14 hertz, it is difficult to approximate by Rayleigh-Jeans. So we consider the entire black body spectrum, the Planck's law. So we consider that the spectral radiance B nu, function of temperature, given by this expression 2h nu cube over c square 1 over e to the power h nu over kt minus 1. So this entire thing is coming out to be 1.46. So you have all the other values given. H is a Planck's constant, c is also a constant, speed of light, k is Boltzmann constant, and nu is given. Nu is nothing but 10 to the power 3.33. Nu is given as 3.33 in 10 to the power 14 hertz. And and intensity is also given 1.46 10 to the power minus 28. This entire thing, So if you put all the other values together, you will see now we can solve for kt or T, and finally T comes out to be 322 Kelvin or 120 degree Fahrenheit. So in the next example, what we are looking at is in an article about a visible light, visible wavelength, spectral observation of a nearby galaxy, the measured flux density centered at a wavelength of 4250 angstrom and with a bandpass of 50 angstrom is reported to be 2.3 10 to the power minus 8 watt per meter square per angstrom. Meanwhile, a radio observation of the same galaxy at 22 gigahertz with a bandwidth of 50 megahertz yields a flux density of 42 Jansky. So there are two bands, visible band and radio band. The invisible band, the wavelength is mentioned, the bandpass is mentioned, and the flux density is mentioned in terms of watt per meter square per angstrom. And in radio, the same thing is mentioned. 22.2 gigahertz, bandwidth of 50 megahertz, and the flux density of 42 Jansky. In which band does this galaxy have a larger flux density? Compare the detected fluxes in the two bands. It's a very interesting question. We first note that the conversion between f lambda and f nu is the same as between I nu and I lambda. So f nu is lambda square over c times f lambda, and is given by this scaling. Just put those values and finally you get f nu as 1.38 10 to the minus 29 watts per meter square per hertz. And f lambda is given in terms of f nu, so that is in terms of angstrom. Okay, so if you just convert each other's, you can get back to this. So we converted the f lambda in the optical to f nu in the radio, and we converted the f nu in the radio to f lambda. That was the exercise we did in the first place. This is for the radio. It was reported in f nu, so we converted that to f lambda, and in the optical it was in f lambda, and we converted that to f nu. The detected fluxes are given by multiplying the measured flux densities by the bandwidths. So if we do that, the f is multiplied by the bandwidth, which is 50 in the case of the radio, with 4.2 to the minus 26 times 50 megahertz is given 2.1 to the minus 18 watt meter. Similarly, if your watt per meter square, and if you're doing for visible, it's 2.38 into the power minus 8, so that is 1.15 10 to the minus 26 watt per meter square. So you can clearly see that the density flux is much brighter in case of optical than the radio. So the next question is about the Orion Nebula, which is the H2 region containing hot ionized gas that emits thermal radiation. At a frequency of 400 megahertz, the Orion Nebula is found to have flux density of 220, about 200 Jansky, and comes from an area of the sky which have a solid angle of 2 times 10 to the minus 5 steradian. Use this data to infer a lower limit to the temperature of the gas in this nebula. First of all, there is a typo. It should be 200 Jansky. And so, if it is 200 Jansky, you have a steradian 2 minus 10 to the minus 5 steradian. So I nu is given by 200 divided by the steradian, and so we have done similar problem before. So it comes out to be 10 to the power 19 watts per meter square, Hertz inverse, steradian inverse. Now, what we do is we know what is a Planck's law. So I nu can be equal to 2h nu cube c square 1 over e to the power h nu kt minus 1. Now that basically says that this for the lower limit of the temperature, so everything else we knew except temperature. So if you substitute that in this expression, all the other values, h we know from before, nu we know, nu is around 400 megahertz, c is a constant, so everything else is known except the temperature. Boltzmann also is a constant. So if you substitute everything in, just remember this value of I nu is less than equal to this Planck's equation given by that. And so that gives you an upper limit, a lower limit for the temperature of the gas, which is 2040 Kelvin. Okay. The next question is a radio observation at a wavelength of 6 centimeters yields determination that a particular radio source has a solid angle of 7.18 times 10 to the power minus 6 steradian, is opaque and thermal, and has a flux density of 350 Jansky. What is the temperature of the radio source? What is the intensity of this source at 2.7 centimeter? Flux density is measured at 6 centimeter, which is still in the realm of Rayleigh-Jeans approximations. So T, we just take F nu as 2 kT over lambda squared times the steradian. We just substitute all the values and get the value of T to be equals to, is the brightness temperature, to be equals to 63.6 Kelvin. At a wavelength of 2.7 centimeter, the frequency becomes 11.1 gigahertz. So the I nu is given by 2 kT over this thing. So and then finally the lambda value is given, the T value is given. So if you substitute all of them, then you get the I nu at this frequency to be equals to 2.41 10 to the minus 18 watts per meter square per hertz per steradian. So that was an easy problem, just a simple substitution. So if you are confused, there are more and more examples we are doing here for your benefit. A spotlight, the next question is, a spotlight has an intensity of 2 times 10 to the power 11 watts per hertz per meter square per steradian at a frequency of 5 10 to the power 14 hertz. What is the brightness temperature? This is a bit higher in frequency. 10 to the power 14 is a bit higher frequency for Rayleigh-Jeans approximation to hold. So you have to write everything in terms of the Planck's law. If you put it like that way, there is a intensity and there is a frequency. So all you need to is to solve for the brightness temperature, and that comes out to be 2100 Kelvin. So its Rayleigh-Jeans does not hold. So you cannot have Rayleigh-Jeans law do not hold at this frequency, because frequency is to the power of almost 10 to the power 14 hertz. That's why. So you put the entire thing into the normal Planck's law and you get the answer. Our next example is that of the Haystack Observatory run by MIT has a small radio telescope, SRT, with a diameter of 2 meters and can observe at wavelength of 21 centimeter or 1.4 gigahertz about, with a maximum bandwidth of 1.5 megahertz. If it has, this is the SRT, if it has the optimum age taper, calculate the following. If it has optimal edge taper, then you can calculate the following. The angular resolution in degrees, the maximum collecting area, the maximum detected power from a 1 Jansky source located at the peak of a side lobe. So those are the 3 questions to be asked. So resolution of with optimum edge taper has theta full width half maxima, or HPBW, the same thing, is 1.515 divided by the D. Also the lambda is there, I believe. Yes, there's a typo. So if you put all of them together, you get the FWHM is 6.92 degree, which is also the half power beam width. They're the same thing. We are given the H taper, but not any information about the physical blockade by the feed horn on receiver, not about the imperfection in the reflector. So maximum collecting area is a geometric area pi r square multiplied by 0.82 due to the H taper. That's due to the H taper. We have then the maximum effective area is 0.82 times pi times 1, because it's diameter is 2 meters, so our radius is 1 meter. So H taper introduces inefficiency of 0.82 or 82% efficiency. At the center of the beam, the maximum edge. So for the effective area becomes 0.82 times pi r square. R is d by 2. D is 2 meters. So R is 1 meter. You put all the values in, you get 2.5 meters square. 58 meters square. Sorry. Third question is, at the center of the beam, the maximum detected power due to a 1 Jansky source in side lobe becomes, so power is P, 1 Jansky source is in the side lobe, so, and then this is times the effective area times the bandwidth 1.5. This is the delta nu, this is the effective area, this is the conversion, Jansky to watt meter square dot. This is it's a 1 Jansky source. So this is the source flux density, and you have a reduction of 0.4% because you're now detecting in the side lobe. So that's the reduction, because it's not in the main beam, but it's in the side lobe. So if you're having a source coming in the side lobe, then the flux density goes down further. In this particular case, it is 0.4% of this. So finally, the power is given by 1.55 10 to the minus 22 watts. So tricky thing over here is to figure out this factor, which comes from, of course, the actual thing. Here we are doing this just to make you aware of the fact that if a source is not coming into the primary beam but coming through the side lobe, so we have discussed this. So if you got the primary beam, and then this is the null, over here is the same thing. So if you draw that, this is the center, this is the P naught, which is the maximum value. If it comes to P naught by 2, that becomes this half power beam width. And then the first side lobe. So first side lobe, the maximum value is much lower than the P0. So in this case, we are assuming this is normalized. This is 0.004 times P0. So whatever the value is. Okay. Next question is, assume that the SRT, the small radio telescope, which we discussed in the previous example, is a prime focus telescope of 2 meter diameter and has an RMS of the reflector irregularity approximately 0.7 centimeter, and that total loss due to the blockage due to the feed and receiver feed legs is 12% of the collecting area. Assuming optimal feed taper, again observation 21 centimeter with a bandwidth of 1.5 megahertz, calculate the following. The effective collecting area, the A effective, detected power when observing a source 1 Jansky at the center of the beam, different from last time. So you can assume that the reduction of the efficiency further, you had 0.82 before, you have include the other 12%, so the blockage introduces a factor of 0.88. So if you go by the expression, you calculate the further reduction, and so the effective area, effective further reduces to 1.19.91. Remember the last time it was 2.58 with just the tapering, and now it is 1.91. It was in the previous example, it was 2. Some problem. It was 2.58 in the previous example where there was no reduction of 12%. So if further reduction of 12% happens, so it becomes 1.91 meters square. Detected power is nothing but 1 Jansky. This is minus 26 times 1.91, the effective area, times the bandwidth, and this gives you this thing. Total power is the total flux density. 1 Jansky is 1. So it is the power is given by 1 Jansky. So 1 times 10 to the power minus 26 times those watt per meter square, etc., times the effective area 1.91 times the effective bandwidth, which is 1.5 into 10 to the power 6. So that effectively finally comes out to be 2.86 times 10 to the power minus 20 watt. Okay. Question number 13. Consider a sequence of 3 amplifiers with the gains of G1 is given by 100, that is 20 dB, G2 is 20, that is 13 dB, G3 is 2200, that is 23 dB, and noise temperatures of 20 Kelvin, 100 Kelvin, and 500 Kelvin. Calculate total gain, total noise temperature of this sequence. Total gain is multiplication of total entire thing. So it is 4 10 to the power 5. That's the in linear unit. In decibel, it is just the addition of them. So 56 dB. So gains are just G1 plus G2 plus G3 in dB, of course. And in linear scale, it is the multiplication. Total noise temperature will be given by Tn is 20, the first one. That is Tn1 plus Tn2 is 100 divided by the gain of the first one. So it is like this. It is Tn1 plus Tn2 divided by the gain of the first one plus Tn3 divided by the gain of the first multiplied by the gain of the second. Okay, so like that. So if you put that in, it finally comes out to be 21.3 Kelvin. That is total Tn. We discussed this in one of the examples previously also. So now a radio telescope has a receiver with total noise temperature of 100 Kelvin, total gain of 10 to the power 8. This is 10 raised to 8. This is in superscript, sorry. And a bandwidth of 1 megahertz. What is the total noise power detected? So total noise power detected will be the gain times the Kelvin in Boltzmann, the K in Boltzmann constant, times the bandwidth times TA plus Tn. Okay, so total gain is given, or this is given. Total gain we have written G is 10 to the power 8, then the Boltzmann, then the bandwidth, and then 100, which is the noise temperature. Okay, because this is goes to 0 for just the noise, and so this becomes 10 to the minus 7, 1.38 10 to the minus 7 watt. This is the noise power, or PN. Question number 15. The radiating element shown in this figure is of 10 meter length and carries a current of 1 ampere. It radiates in theta equal to 30 degree direction in free space at frequency f given by 3 megahertz. Estimate the magnitudes of E and H at a point located at 100 km from the point of origin. This is regarding the radiation. So at 3 megahertz, lambda equal to 100 meter, as long as the length of the element remains less than or equal to lambda by 10, the field components are given by the previously we have done. So you can derive the field components from there, and since only those field components which are inversely proportional to the R contributes, so we have discussed this at very large distance, R squared and R cubed terms vanishes or goes to 0. So at very large L, ER will go to 0. E theta has 1 over R term. This too will go to 0. The term which survives is this one. For H pi, again the second term, the first term in this case goes to 0, and the second term survives. Okay, so these are the two terms which survives as R tends to infinity. So E has a theta component and H has a phi component in this particular case. Okay, so what it happens is that if you write it down in this expression, that is all there. So finally, if you now goes for the value of theta as equal to 30 degree, so sine 30 is given, and I is let's go back and check. Sorry, the I, the length is 10 meters, current is 1 ampere, theta is 30 degree, and frequency is 3 megahertz. Okay. So if you put the values of so DL, all these values if you put in, you finally get the value of E given in terms of 45 to the 19, and H is given in terms of this. Put in the values, you get the answer. Not very difficult. The last of the problem today we are discussing is calculate the distance at which the electromagnetic wave will have the same magnitude for induction and radiation fields if its frequency is 10 megahertz. So the induction and radiation fields will have the same magnitude at a given R, given by frequency over the circular frequency, and that is so this is the C over the circular frequency. So this is given by 3 10 to the power 8 divided by 2 pi 10 times 10 to the power 16. This is 10 megahertz. So R is given by 4.77 meters. So R is the distance which is given by C over omega, C over 2 pi nu. Nu is 10 megahertz, C we know, so if you put the value you get finally 4.77 meters. That's the answer. Okay. So that brings us close to today's session of additional problems. I hope this helped a little bit to your for catching up to the material which has been covered so far, and we will keep interacting in the live sessions and try to come up with more solved problems which can help you in understanding the concepts better. So thanks for joining. Thanks a lot. Hope this helps. See you in the next class. Thank you.